Titration practice problem. In this video, I'm going to tell you particularly about an example in which we are titrating a weak acid with a strong base. So this is my sample, this is my titrant. One of the purposes of this is basically trace or keep track of how the pH of your sample changes as you're adding more and more of the titrant. So the pH is really registered for your sample. The volume that you're adding here in this axis is the volume of the titrant that you are putting into this flask. For this particular problem, we have a weak acid. Look at K value, lower than 1. We're also given its concentration and initial volume for this flask. And then for the strong base, in this case the titrant in the burette, is going to be given by the concentration and different amounts of the volume that we are adding to the sample of the weak acid. So we are going to be allowed to construct this plot by finding what are the different pH after the addition of different amounts of the strong base. So warning, this video is not to show you how to do acid-base problems. This video is just to actually show you or guide you in identifying what kind of acid-base problem you're going to find along the path of this process of titration. We have different regions at the very beginning of the titration. Basically, you haven't even started the titration. Before the equivalence point, certain amount of the titrant has been added. What happens at the equivalence point, and then what else happens if you keep adding more of the titrant after the equivalence point. So I'm going to help you identify the different types of problems that you have here, but it's not about solving these acid-base problems. I'm assuming in this case that you are familiar with how to solve the different kinds of acid-base problems that we know. So let's begin with the very first point. 0 volume of the base that it's being added corresponds to this 1 point. Really, in this case, you have not opened this from the burette, so there's no base coming in contact with your acid. This flask, the pH of this flask is going to be only given by the Ka and the concentration of this weak acid. This is a regular weak acid equilibrium problem. We know how to solve this problem through the raised table. Initial concentration is given in our problem already. Initial concentration of the conjugate base is equal to 0. This is approximately equal to 0. Remember, the sources of H+ in this case are only that coming from the auto-ionization of water. So we look at the changes given by the amounts of dissociation of the acid or ionization of the acid, the production of the conjugate base, the production of H+ coming from that dissociation. We find the concentrations at equilibrium. And then another thing for this video, I'm not going to use any approximations to solve this problem. You can try these approximations on your own, see how simpler the problem can be, but do not forget ever to check the validity of your approximations. Checking, that's always very important. So here I'm going to solve the full quadratic or cubic equation depending on what I get. And then I'm going to get those values for x in my rise table. First equation, the Ka expression in terms of the concentrations of all these species at equilibrium. We substitute the actual values. The concentrations in this case will come from my rise table at the equilibrium state. Then I end up having a quadratic equation that if I go and solve, I get this number. This x, according to my table, represents the amounts of the conjugate base, but also the amounts of my acid, in this case, or the H+. So if I know already the amount of H+, I can directly calculate pH equal minus log of this x, concentration of H+, and I end up having 1.95. Have that number in mind because that's going to become very important. 1.95 is the very first point when we have not added any volume of the base. This is just the pH of the initial sample that I have on this flask, the solution of my weak acid, 1.95. Second problem. Let's see, we are adding 5 milliliters of sodium hydroxide. So now we are entering this region where we actually have some of the base coming in contact from the burette into my flask. They're going to react. I have an acid and a base. So this is a stoichiometry problem, acid-base reaction. The limiting reactant in this case is always going to be the titrant. We're going to see how that is, but it's always the titrant, the one that is the limiting reactant. So for this problem, what we have to do is to determine the molar amounts of both the acid and the base that are available for the reaction. We calculate that, number of moles. Remember, we have concentrations and volume. We multiply those, we get number of moles. In this case, for the acid, 5 10 to the minus 3 moles. You also can express that as 5 millimoles. For the base, concentrations times the volume that it's being added gives us 0.5 10 to the minus 3 moles. That's going to be 0.5 millimoles, another way to express it. So now, next step is to determine the type and amounts in number of moles of the products that we get after the acid-base reaction has been completed. For this, we're going to use this table that I call BARF table, some sort of a silly name, but hopefully that sticks in your head. This is about amounts in number of moles or millimoles. Amounts, that's what you have here. The beginning amounts, the amounts involved in the reaction, and the amounts at the final point of your reaction. Okay. So the beginning amounts are given by this that we calculated: 5 millimoles of the acid, 0.5 millimoles of the base. We can identify immediately that the stoichiometry is 1 to 1. So if I have 5 millimoles, I will need 5 millimoles, but I only have 0.5. So that means that the base is the limiting reactant. Because it's the limiting reactant, it's going to be fully consumed during the reaction. So if you started with 0.5 millimoles, 0.5 millimoles will have to react. And this amount is what determines how much of the acid is reacting, and it's also determining how much of the conjugate base is being produced. At the end of the reaction, this goes to 0, limiting reactant, and this is just the final amount is what happened, what you have at the beginning minus whatever it reacted, in this case 4.5 millimoles. For this one, you didn't have anything at the beginning, you produced 0.5, the total amount at the end of the reaction, 0.5 millimoles. So now here, what we have at the end of the reaction between the acid and the base, the final composition of my flask is a weak acid plus the conjugate base that was produced. Whatever weak acid I have left after the reaction plus the amount of the conjugate base that was produced. So this sounds like a buffer. If it sounds like a buffer, then maybe we can use the Henderson-Hasselbalch equation. So let's try and see how that goes. The Henderson-Hasselbalch equation, HH equation, is here. You should remember this equation is very important. It applies for systems that we consider buffers under certain conditions. So we're trying it here, see how it goes. Substituting the right amounts in this case lead us to have a pH of 1.90. Wait a second, 1.90. So the first point here was roughly 2 because it was 1.95, but now what I'm saying is that the pH actually decreased after I added the base. That doesn't make any sense. If I'm adding some base, then the pH should increase. The pH should go up as I am putting more base, the titrant, into my weak acid in the flask. So if this is not happening, that means that the HH equation is not giving us accurate results. So there's something wrong why we cannot use this equation. There must be something wrong. So what is that? Just let's go very quickly to check. We have the weak acid and its conjugate base. It's a principle, a buffer. The question is, can we use this HH equation? It gave us a really bad result, so we're trying to find out why. Remember that this Henderson-Hasselbalch equation, it's actually an approximation, and it's only generally valid whenever you have the ratio between the concentrations of the base and the acid somewhere in an interval of 0.1 and 10. In this case, remember this interval 0.1 to 10, in this case what we calculate is that it's equal to 0.11. So we are getting really close to the boundary that it's actually making valid this equation. We're getting on this side of the boundary. Another reason that maybe it's suspicious that this equation is not giving us the results that we were expecting is that the pKa is actually 2.85, and it's known that the best interval of pKa values is something in between 5 and 9. Now, let's be careful here. It doesn't really mean that because the pKa is outside of the better values of pKa, it does not mean that then this particular problem cannot ever be solved using the HH equation. That's not what it means. What it means is that if this were in this interval, it will be much better. But this one can still be used if certain conditions of the ratios between the concentrations are met. In this case, we're very at the edge, plus this one is not really in this interval, so it's a double lose in this case. So it's not a win-win situation. It's losing situation from any point of view that you want to see it. Actually, yes, when we tried it, it fell. We went with it because supposedly this is still within the range, so we went and used the equation, but we know that according to the result, this equation is actually failing us. So what do we do now? If we cannot use the HH equation, one thing that we can always go and do is solve this problem the most general way, which means using a Rice table, the general approach of solving an acid-base equilibrium problem. So for that, we're going to go and use the Rice table. Remember, Rice table uses concentration, not amounts in number of moles or millimoles, but concentrations. So we calculate the concentrations given this new volume. We had 50 milliliters at the beginning, but then we ended up putting 5 milliliters of the base. So 50 in here plus 5 from this one, you ended up with 55 milliliters of the total solution in the flask. So this is the volume that we are using here. So now we go and check our Rice table. This concentration is the concentration that you have at the beginning, the initial concentration in your Rice table, this one for the acid, this one for the conjugate base. In molarity, we do proceed the same way as we did before with minus X for the reactants because the concentration is decreasing, plus X for the products because its concentration is increasing. We end up having the concentrations at equilibrium. We set up the equation of Ka in terms of the concentrations of each of the species at equilibrium. We ended up having a quadratic equation that if we solve is going to give us 6.67 10 to the minus 3 molar. That X is the concentration of my H+. Then now I have 2.18. So this problem now is telling me that at the beginning I had 1.95 as a pH. My second pH will have to be higher, and that's exactly what I'm finding. So this one, the pH increases with the addition of the base. That's what we were expecting. This way of solving the problem is actually good, whereas the HH equation does not apply in this region. So what you can see now, look back at this equation, at this plot here. There are two regions here. The first region at the beginning of the titration where the pH changes drastically, or at least more drastically than after you enter this region that we call the buffering region. Once you are in the buffering region where the concentrations of the acid and its conjugate are in a good ratio such that the buffer is actually very effective, then the pH doesn't change as much as whenever this ratio makes the system not an effective buffer. And that's what we're having here. Okay, so that's why this Henderson-Hasselbalch equation also didn't work, because we're more in this region than in the region where clearly the buffer power is effective. So in summary, if you don't know if the Henderson-Hasselbalch equation is giving you the right result, or clearly is telling you something that it's not making sense, then you can say the Henderson-Hasselbalch equation does not apply at this particular point on the titration, but I can solve the problem by using the approach, the general approach of acid-base equilibria with a Rice table. Last point that I'm going to do here for commenting on this video is what happens now if I add 20 milliliters of the base. Still, now we're adding more of this base. By the way, this is just a representative plot, is not corresponding to this actual problem. This is just for you to look at the general shape. But this is still going to be an acid-base reaction with a limiting reactant. We have to proceed exactly the same way as we did before. We determine the molar amounts of both the acid and the base that we have available for the reaction. We know from the beginning that we had 5 millimoles of the acid. Now we calculate 2 millimoles of the base that are being added. We have to determine the type and the amounts in moles after the reaction between the acid and the base where is completed. We use the BARF table, again, beginning amounts, amounts during the reaction, and final amounts for the reaction that was completed. We substitute the values 5 and 2. We know that this is the limiting reactant according to the stoichiometry. This one determines how much of the acid is being reacted. It also determines how much of the conjugate base is being produced. We end up with 0 for the limiting reactant. We end up with the combination between in the flask. The final solution will contain a mixture of the weak acid and its conjugate base. So now we have the same composition, weak acid, conjugate base, buffer in principle, so we can calculate. Now the question again is, can we use the HH equation to calculate the pH of this buffer? I want you to try these two approaches. Use the HH equation, assuming that this is a buffer, and then you are in a certain conditions that allows you to be in this buffering region where the pH is given with good approximation by the HH equation, but also do the Rice table to confirm that if the HH equation works, then doing it with the Rice table should give you pretty much the same result. There's always going to be certain differences because this is an approximation, this is more exact, but then if the approximation is good, the result from these two different approaches should be the same. So let me know if you have questions, if you have comments, but again, this is one of the problems that you can set up for titration. You can keep going on with all the other different amounts. Let me know if you have questions about how to set up the other ones, but this is the one problem that I wanted to comment with you today. Have a good one.